So in the last lecture, we have been discussing about the different current components in a transistor. So we have seen that externally, we can see only three current components: IE, IV, and IC. But because of different physics happening inside the transistor at the two junctions, one at the emitter side, another at the collector side, there are different current components from inside which we can look into. So the main components are shown over here. Just starting from the emitter junction. Actually, we can just, before proceeding, let us see the kind of biasing here applied makes this transistor in normal operation mode. That is, emitter junction is forward biased, and this collector junction is reverse biased. Okay, so at the emitter junction, carriers are being injected from emitter into the base, that is holes here, and the carriers from base, they are actually injected into the this emitter. These are the electrons here for this case. So these two components form this current IPE and INE respectively. IPE and INE. Now a part of IPE is recombining into this base, forming this current IPE minus IPC1, and rest is being collected is equal to IPC1 by the collector. We have already seen once the carriers which survive without recombination are and reach at the collector junction, they are collected by the collector. At the collector junction, on the other hand, due to the thermal agitations, there may be electron hole pairs generated inside the wide depletion region, and there may be some carriers also from the base and collector, the minority charge carriers, which may eventually come in the contact of this depletion region and form the currents called as IPCO and INCO. Okay, so in this way we can see the different current components and different terminals, which can be combined together to just represent the currents, okay, which flow through this IE, IB, and IC. So here we can see that ICO is similar to the reverse saturation current. Okay, this is reverse saturation current of PN junction. Okay, so ICO is that one. So this is corresponding to the collector junction. That's why we write here IC. O is just showing that it is saturation current. Also, sometimes it is related that when emitter junction is open, okay, when emitter junction is open, that is there is nothing happening on the emitter junction. We are left with this collector junction only, and this is the current flowing through this collector junction. So we can write these different equations for the collector current. Say we have just seen that a part of emitter current here we can see that emitter current is actually comprising of two components. One is due to the hole injection and another is due to the electron injection. So electron is injected from base into emitter, whereas the holes are injected from emitter into base. So emitter we have seen is heavily doped. Okay, this is heavily doped and this is lightly doped. Base is lightly doped. So a large quantity of the carriers are injected from emitter into the base rather than being injected from base into emitter. So INE is most of the times assumed to be negligible. Okay, so INE is negligible, and we say that IE is almost equal to IPE. So a part of this IP is being recombined to the base and rest is collected by the collectors. So we say that this IC is mostly depending on this IE. Okay, this is proportional to this IE, we can say, and we remove this sign of proportionality. I'm sorry, this is IE. IC is proportional to IE. If we remove this sign of proportionality, then we say that a part of this is being collected. Okay, so that part which is being collected is represented by alpha here. Apart from this part of this uh, uh, carriers injected from emitter into the base, some current always flows through this collector junction, even when it is reverse biased, that is reverse saturation current ICO. So the algebraic sum of these two current components form this collector current. Okay, so that's what it is written here. Also, we wrote this alpha in a different form in the last lecture. That alpha can be written as IC minus ICO upon IE minus 0 with a negative sign. Okay, so alpha is also defined as large current gain. So IC is the current when we have emitter current IE, and when emitter current is 0, then we have say corresponding IC current to be equal to ICO. It is not 0. So the ratio, okay, of these two changes in the current, okay, so it seems that there is a change in IC divided by change in IE. Okay, so there is a large change in the IC when there is a large change in the IE. Okay, so this ratio is defined as large current gain. So others remarks already we have gone through in the last lecture. So if we only look at the whole current component, then whole current component we can see which is forming this collector current IPC can be written as IPC1 plus IPCO, whereas in the IC current the contribution to the electron current one can write maybe INC, and that will be equal to just INCO. Okay, so Again, one will see here that the current, this INC or this INCO, enhance, and IPCO, this is very small. Okay, so we will see that most of the time this will be also neglected. Now we can write the generalized transistor equation. IC is equal to ICO minus IPCO. I already discussed. This is valid only in active region of operation. The normal mode, okay. So the normal mode of operation, normal mode is also called as active, in which emitter junction is forward biased and collector junction is reverse biased. So for generation, we can write the PN junction equivalent equations. The emitter junction is forward biased, so we can write the current through this emitter junction in terms of this diode current equation. And I naught, we can relate it with this reverse saturation current flowing through the collector junction. So the current through the collector junction JC, we can write like this here with VC, the reverse bias voltage across the collector base junction. So IC can be written like this here. So IE, okay, in other way, IE can also be written as I not into this in the form of diode current equation. Okay, diode current exponential V. So in here it may be replaced by BE, the emitter forward bias voltage, BT minus 1. Okay, so this IE can be understood to be the diode current. Similarly, the ICO is going to vary with the collector voltage, collector junction voltage. Okay, so that can also be written like this. So we can generalize this in this way. So the different current components re-illustrated here. This is for NPN transistor. So collector and emitter both are of N type here, and base is P type. So the arrows here shows the direction of the charge carriers flow here. That is, electrons, majority electrons are flowing from emitter toward the collector. And we know that the opposite direction to the flow of negative charges, that is the reference direction for the current. Okay, so that's why the current directions are shown here like this. These are the actual current directions, IE, IC, and this IB. Okay, so here if we assume this transistor to be as a node here, then IE is equal to IC plus IB. We can apply the Kcl equation here and write the current equation, equation for this transistor. I is equal to IC plus IB. We can see that this equation is valid even for the PNP transistor. Okay, so either we take PNP transistor or we take NPN transistor, it is valid for all the transistors. I is equal to IC plus IB. So this equation we can write always valid for NPN or PNP transistors. I is equal to IC plus IB. The collector current is comprising of two current components we have just seen. Okay, one we can call is as majority current component, and another is due to the minority current component. Okay, so majority we have seen is proportional to IE, and this is proportional to this reverse bias collector junction. So we can take here say PNP transistor. This is PNP transistor. Already we have seen that majority carriers are flowing from emitter towards the collector, and there are minority charge carriers also which may flow from collector towards base, and okay, and these together may form the minority carrier current. So that minority carrier current is nothing but ICU, okay, having two current components, INCU and IPCU. So this thing can be also just illustrated like this here in the left diagram, and symbolically we can represent the same situation in this way. So it is always not convenient to draw the transistors showing their regions P and these regions P and P. So we use the symbols here, okay, for compact representation, and an arrow in the base emitter leg is important here. So this is symbol for PNP transistor in which the arrow is going into the base, okay, from the emitter. Similarly, we can see that for the NPN transistor here. So the arrow is from base into the emitter, okay, for this. So these are showing here the current directions. The charge carrier, okay, the electron we have seen that is emitted from emitter into the base and then collected by the collector. But the reference current direction, okay, this is the reference current direction which is opposite to the flow of the electrons, okay, negative charge carriers. So actual current direction is from right to left for NPN transistor here, where for the PNP transistor it is from left to right in this case. So transistor is able to transfer the current over the different resistances, okay, that makes it to work like as amplifier. So the foremost application of this transistor device is as an amplifier. This situation is illustrated here, how it is working as an amplifier here. So looking at this transistor symbol, we can conclude here that this is PNP transistor. So emitter is made of P type, base is of N type, collector is of P type. And looking at the type of the biasing applied at the in between the emitter base junction, it is forward biased, and that if we look at the voltage between the collector and base, then it is reverse biased. Okay, so in current here is IE current is actually flowing through the emitter. A part of this is going to be collected by collector majority, and some part is going to be flowing through the base. That's what we have seen in our earlier discussions. IE is equal to IB plus IC. IB we have seen that is going to be small. Why it is small? Because base is narrow enough, recombination is less, base is lightly doped, so less carriers are being injected from base into the emitter. So all these shows here that IB is very small, and in the most of the situations we will see that our IC is almost equal to IE. Okay, because IB is small. Okay, IB if say is of the microamperes order, then IE may be of the milliampere order. Okay, so there may be thousands of orders difference, and that's why we can neglect for simplistic calculations. Okay, only we can neglect the IB. It is not always advisable to just ignore IB, but for most of the cases we can see. So suppose here there is a small voltage change in input voltage, that is input voltage. Let us see where it is. So looking into this case here, this side seems to be input here, and this side seems to be output here. Okay, so we are giving some signal from the this emitter base junction side, so that from the input side, and we are connecting a load resistance at the collector between collector base. Okay, so that is forming this output side. So if there is a small change in the input side, that is between the emitter and base, if there is some change in the input voltage, then because this is forward bias. Okay, base emitter junction is forward bias, there will be a large change in the current. We have related little while ago that IE is exponential VE by Vt minus 1. Okay, like a diode, it is having a diode like behavior, and given that emitter base junction is forward bias, so if there is a change, a small change in the input voltage is here is nothing but BB voltage. Okay, this is BB voltage is forming the input voltage BI. So current I is going to change by a huge amount here, and this huge amount in the current I change will make that a larger component of this IE is going to be collected by the collector and passed to the output load. So because there is large change in the IE, so we can expect there is large change in the IC as well. Okay, so this is what forms the basis of the amplifier. Now change in the output voltage across RL, we can see to be equal to RL times change in the IC. Okay, so we changed the input voltage, that resulted into a change in the IE, that makes a change in IC, and output voltage, that is here VL. VL is nothing but RL into IC. Okay, VL is equal to IRL into IC. So change in the IC, change in IC makes a change in VL. So we can write this here. So now we can see that voltage amplification. Okay, if we define as the voltage amplification, then change in the load voltage to the change in the input voltage. This will be defined as amplifier gain here, or amplification. So delta VL we can write here alpha dash RL delta IE upon delta VI. So we see here that the catch is here, okay, that RL times delta IE here. Delta IE, actually we see here that alpha factor was very close to 1. It was having 0.98 typical values like that, okay. Large current gain. In the last lecture, I think we have seen that alpha should be very close to 1, that the transistor should be so designed that most of the currents injected from the emitter should reach the collector and should not recombine in the base. Okay, so most of the carriers should reach. So alpha is very close to 1. So what we are left with is uh, RL times delta IE upon delta VI. So Vi is going to change by a small amount. So there is a large change in the delta I, okay, in the emitter current because of the exponential relation already we have seen. So that's why we see that the gain is going to be greater than 1. Uh, One more thing here we can relate that emitter junction is forward biased. Okay, so this may be assumed to give a dynamic resistance Re. So dynamic resistance Re we have defined as uh, del Vd upon del Id. Okay, so this can be defined as 1 upon del Id upon del Vd. Here Vd we are just relating this with the diode uh, parameters here. So ID diode current we have seen to be equal to I naught into exponential Vd upon Vt minus 1. Okay, so from here we can see here. So now in place of this ID we are having this IE, okay, and in place of Vd we are having Vi here. So actually rewriting this equation, alpha RL minus alpha RL. So we can write here delta Vi upon delta IE. Okay, so this equation can be rewritten here. So this value delta Vi upon delta IE is equivalent to Re here of the forward bias emitter junction. So we can write this as alpha RL upon Re. Re, we have seen the dynamic resistance of the forward bias junction to be very small, of the order of say uh, few ohms, like 10 ohms, 50 ohms, but not larger than that. Whereas RL we have in our hand. RL can be fixed to of the order of kilo ohms, whereas Re is of the order of few ohms. Let us say that 10 ohm, and alpha is very close to 1. Okay, so the gain A will be 1 times say 1k divided by 10. So here you can see around 199 it is typical to get the gain around this. If we fix this load resistance RL in this way, of course load resistance we can increase to a larger value, and so the gain can be also improved. But it is not like that we should use say mega ohms of load resistance, and then also we will be getting such a high amplification factor. There may be some other things which may come into playing, okay, and may reduce the actual gain. So ultimately we see here that gain we can get because of the transistor actions here, that almost the same amount of emitter current is okay, is there is a change we can see in the collector current also, okay, at the output, and this makes it possible to have a gain. The typical values of Re already we have seen is equal to almost 26 upon IE. Bt we have seen was 26 millivolt. So 26 divided by IE, and here IE is in the milliamperes. Okay, that's why it is having this nice shape. So parameter alpha dash is defined as the ratio of change in the collector current to the change in the emitter current at constant collector to base voltage, and is called the negative of the small signal short circuit current transfer ratio. So alpha dash is defined like this here. So for a given BCB, the ratio of the change in the collector current to a change in the emitter current, that is defined as alpha dash. So alpha is depending on something which is happening inside the base due to the recombination. So for the most of the cases, we can assume that this alpha is independent of IE, and we can write the alpha to define like this, which already we have seen. So alpha dash and alpha, these seems to be same value here. So alpha was large current gain, and alpha dash here, which is defined as change in the collector current to the change in the emitter current. Okay, whereas this was not a change, this was the absolute value. Okay, the DC voltage, and sorry, DC current. So if we fix some biasing voltage in the on condition of the transistor, so corresponding to a biasing values of the voltages at collector junction and emitter junction, we have IC and IE, and when we keep the emitter open, there was a current through the collector given by ICO, and this was given as large signal gain. Whereas here this alpha dash is actually we can see is related to the change in the collector current and change in the emitter current. So this is something uh, related to the small signal current gain. So small signal and large signal current gains are almost same here. Alpha dash and alpha, they are same because alpha is independent of IE because of that reason. The transistor is having these three terminals. Okay, we have seen the emitter, base, and collector. Okay, so depending on this, actually we can give input at one terminal, okay, and we can take output at the other terminal. Okay, so for giving input we need one terminal, for taking output we need one terminal. So but the transistor is having three terminals, so one terminal is left. Okay, that is made to be common to both input and output. So in this way we have three configurations. Okay, for the transistors we have three configurations depending on this. So we can give input and we can take output, and the third terminal is made common. So say we give input at base and make the take the output at emitter, and collector is made common. Okay, so this is one. Either we give input at base, take the output at collector, and emitter is made common. And either we give input at emitter and base is made common, and we take output at collector. One thing we should look here that because the collector junction, okay, collector junction is reverse biased, so we cannot give input at this collector junction. Okay, so that's what we can give input at base or emitter, and but we cannot give the input at the collector. Okay, so input we can see is given either base or emitter, and output can be taken sorry, and this is wrong here. Output input is given at emitter, and base is common here. Base should be common, and output should be taken as collector. Okay, so output, yes, output we can take at emitter or collector, but we cannot take output at base. Okay, with a similar reason we cannot take output at base because base is in the middle of this the okay, and base current is very small, and that actually controls that is the base is just as a controlling gate kind of thing here. So we also don't take the output at base. Okay, so output can be taken at either emitter or collector, whereas input can be given at base or emitter, and output sorry, the rest third terminal is made common here. So first configuration here seems to be uh, depending, okay, be depending on the common terminal. We can also write the nomenclatures here, that common collector, common emitter, common base kind of thing. Okay, so we have three different configurations depending on which terminal is kept common here, because that is unique in the common collector. As we can see in the common collector, we can see here that base and emitter are used as input and output. For common emitter here, we are using base as input and collector as output. And for common base here, we are giving input at emitter and taking the output at collector. So in this way, these three configurations we get here. First is common collector here, it seems, then common emitter and common base. Now, from next lecture, we will try to look into the details of these configurations, their uh, some more characteristics here. So here it was starting with common base configuration. Common base configuration, we can see here that input is given at emitter and output is taken at collector. So with this we stop here. We will continue our discussion in the next lecture. If you have any questions, you can ask.